Today's notes are on section 4, which we're going to call ionic bonds and compounds. Up to this point, we've just talked about elements and atoms, and with section 3, we kind of set the stage to predict how they are going to bond, so let's get to it. So how do ionic compounds form? Well, it starts with two oppositely charged ions that combine in ratios such that the overall charge on a compound is 0. That's going to be pretty important. Ionic compounds will have no net charge. Now, each of the ions will have a charge, but they will sum up to 0 overall. It will always be between a metal and a nonmetal, or a group of nonmetals. The only exception to this is if sometimes you see an ammonium ion, which is an H4+1 ion. If you have a metal react with oxygen, those compounds will be called oxides. If you have a metal with metal with a nonmetal, those will be called a salt. So, two terms there, oxide and salts. Binary ionic compounds. These are ionic compounds which contain only two ions that have combined chemically. So these are really simple, right? Binary meaning two, right? NaCl, sodium chloride. If you look on your ion sheet, sodium has a +1 charge, and chlorine as an ion is a chloride ion with a -1 charge, right? That's what's going on for that one. MgO, magnesium oxide. Magnesium's got a +2 charge. Oxygen has a -2 charge. This is going to be sodium fluoride, sodium with a +1 charge, fluorine with a -1 charge. But notice how we write these. We don't write them with any charges. The overall charge ends up being 0. So this one's +1 and this one's -1, adds up to 0. What about ionic compounds that are not binary? Well, what ionic compounds might form from, say, like a calcium ion and fluoride ions. And if you check your ion sheets, you'll see that there is a calcium ion with a +2 charge, plus you know that calcium's in family 2A, so it's going to form a +2 charge. And then fluorine forms fluoride ions, and since it's a halogen, its charge will be -1. Well, remember, the overall charge needs to be 0. So if I just have one calcium and one fluoride ion, what ends up happening is I'd have a net overall still of +1, so we can't have that. So what we need to do is actually put more fluorine into this compound to get the overall charge to be 0. And so I actually need 2 fluorines to do that, so we're going to put the 2 down below there as a subscript. And now you have a total of +2 charge coming from this calcium ion. And since there are 2 fluoride ions now, a total of -2 charge there, and this sums up to 0. Notice we're not writing any charges or anything on the compounds. We don't put it up at the top or afterwards or anything like that. We just need the overall charge to add up to be 0. So let's try something that may not be quite as obvious. What about aluminum ions and oxygen ions, right? These are actually called oxide ions if you check your ion sheet. Aluminum has a +3 charge, and oxygen forms a -2 charge when it forms an oxide ion. Well, if you just have one of each, I end up with a net of +1 overall, so that can't work. And there's no way for me to do this where I have one of either of the ions. I'm going to have to make sure that it adds up to 0. And the only way to do that is actually to find the least common multiple of 3 and 2, which is going to be 6. So if I can get a total of +6 charge from the aluminum and -6 charge from the oxygen, I'll sum it up to 0 charge overall. Well, in order to get +6 from the aluminum, I'm going to need 2 aluminum ions, and then to get -6 from the oxide ion, I'm going to need 3 of them. So when aluminum forms an oxide, aluminum oxide, its formula becomes Al2O3, right? And that would be because with those 2 aluminum ions, I'd end up with a total of +6 charge, and the 3 oxides form a -6 charge, which again adds up to 0, which is what we want. And just a reminder, we don't write it anywhere above it, no charge above the element or the subscript or anything like that. Okay, remember, compounds are always going to end up net of 0. What about ions that include more than one atom? You may notice on the ion sheet there are some ions that are more than just one atom, and these have a special name. These are called polyatomic ions. Get familiar with the list. There's a list on the front and back page of your ion sheet. One side has all the positively charged ions, one has all the negatively charged ions, and then the back side has the list broken down into 3 separate subcategories. You'll need to become familiar with this list. You'll be allowed to use it on tests in the future, but a lot of these things are going to pop up over and over and over again throughout the rest of the year. So you're going to have to start becoming familiar with them. So you've got a sheet, you'll need to start studying them. So for instance, like one of them looks like this, NO3 with a -1 charge. Now notice it's not just one atom anymore, that's why it's called polyatomic. And it adds up to a charge of -1 overall. Okay, this is called a nitrate ion if you're looking at your ion sheet. SO4 with a -2 charge. This is called a sulfate ion. CO3 with a -2 charge. This has a name, a carbonate ion. So when we get to naming here pretty soon in the next section, you're going to need that ion sheet to help you out. Until you get, again, familiar with these, there's going to be quite a few of them, and you're going to see some more commonly than others. Okay, so the physical structure of an ionic compound. Okay, remember we're talking about ionic compounds, which are metals combining with nonmetals. So the physical structure. The positive and negative ions exist in repeating patterns and shapes. Okay, so this one over here, for example, is a picture of a crystal of sodium chloride, right? This would be table salts. These are called crystals, and the actual shape that the ions form is called a crystal lattice. Okay, so there's your vocab word here on this slide. It's a 3-dimensional geometric arrangement of particles. This one you may be able to kind of tell if I sort of dot some stuff together here. Forms a nice, clear, 3-dimensional box-shaped pattern. They're not all going to be like this. Sodium chloride's kind of nice. Maybe now you can see the box shape to it. Sodium chloride's pretty nice for this. They're not all going to be like that, but maybe now you can see sort of its 3-dimensional geometric arrangement, right, the crystal lattice. The shape of crystal varies depending on the chemical formula, right? So this is nice because I have a 1-to-1 ratio of my compound, NaCl, 1 sodium to 1 chlorine. But if you had something, say, like what we saw in one of the previous slides, aluminum oxide, Al2O3, that's not going to fit conveniently into this kind of structure, so it's going to have some other kind of shape. Physical properties of ionic compounds. The melting point, boiling point, and hardness all depend on how strong the attraction between the ions is. Basically, the stronger that the pair of ions are attracted to each other, the higher the melting point, the higher the boiling point, the harder that material is. Electrical conductivity depends on the ability of charged particles to move freely. Well, if we go back and look at that picture from the previous slide with the crystal lattice, those things are not able to move freely. They are locked into position. So we're going to see that these things are not really conductive, at least as a solid. Electrical conductivity. So in a solid state, ions are locked into that crystal lattice. Okay, they can't move around. And therefore, they are poor conductors of electricity. Right? We don't make wires out of table salt, for instance. Okay, it doesn't work. We can't run a current through that. However, if you can liquefy that particular solid, that's solid ionic compound, or if you can dissolve it in, say, water, when you do that, things are free to move around. Right? We talked about what's the difference between a solid and a liquid is, at least on the atomic scale. And so if things are able to move around, well, then electricity can flow. So if you can liquefy that salt, which again takes quite a bit of heat, or if you can dissolve it in, say, water, it will actually conduct well. And we refer to these as electrolytes when they are dissolved. Okay, so Gatorade tries to sell you on buying things with electrolytes. All that really means is that that solution would then conduct electricity. So melting point and boiling point. So ionic bonds are relatively strong. Remember, things like to react because they become more stable. They have a good attraction to other particles. Therefore, ionic compounds have high melting points and boiling points. You can kind of see here sodium iodide. We're going to learn how to name these soon. Potassium bromide, sodium bromide. And we can see as they're going up here, all the way down here to this bottom one, magnesium oxide. And I want to point this one out because this may end up, I don't know, on a future test question. Notice there's a huge jump here. Even though this is a binary ionic compound, we're in Celsius, but this temperature is, almost 3.5 times sodium chloride, right? Even though it's still just a binary compound. And the reason for that, if we've been paying attention to all the ions up to this point, with the exception of this calcium chloride, they're all plus and minus 1 ions, right? Sodium's plus 1 and chloride's minus 1. Well, magnesium chloride is a plus 2 and minus 2 ion. So it's going to have a stronger attraction between the magnesium ion and the oxide ion, resulting in a much higher melting and boiling point. So if you're asked in the future, say, what's going to raise the melting point or boiling point of an ionic compound considerably, the answer would be the charge associated with that. Okay, and hardness of a crystal. Crystals are hard, rigid, and brittle. Okay, brittle simply meaning here that you can't bend it, and if you try to bend it, eventually it's just going to snap all at once. So to break a crystal, force must break the charge between the ions. You actually have to give it enough force to break the attraction between the ions. Remember, opposite charges attract. So in a crystal lattice, okay, you've got alternating positive and negative charges. Again, they're not always in a square formation. They are just here, so it makes the most sense. But if you hit that crystal, let's say, with something like a hammer, in order for it to actually break, what you have to do is unalign the crystal lattice. You have to get the like charges to be next to each other. And when you do that, it's going to repel. Okay, and so when you end up with two separate pieces here, it doesn't bend like a metal might do. It's brittle, so it snaps apart all at once. And when compounds form, these are two important terms that we're going to see this year as we're doing demonstrations in labs. They can either absorb energy, which is endothermic, means energy in. Think of it like that, energy in. Okay, or they can release energy, which is exothermic, which is simply just going to be then energy out. Okay, it's leaving. Things that are exothermic let off heat. These are hot. Things that are endothermic, when they react, get cold. And for ionic compounds, remember there are other types of compounds, but for ionic compounds, formation is always exothermic. In fact, considerably so. Some of them let off tons and tons and tons of heat. So we generally don't do them here in lab. And if we do, they are very carefully monitored and in a controlled environment. But these are always exothermic and release quite a bit of energy. So that does it for this section.